Hey everyone, welcome back to Collapsed Latents. This week in AI, your weekly deep dive into the most groundbreaking, mind-bending research shaping the future of artificial intelligence. I'm your host, and this week, we're not just seeing progress, we're seeing paradigm shifts. 5 papers, 5 revolutions. From tiny models that outthink giants, to AI agents that research like scientists, to an AI that plays Genshin Impact like a pro, and even one that becomes the villain. Stick around because this week, the future of AI isn't just smarter. It's more human. VibeThinker 15B, the tiny titan that outperforms giants. Let's start with a model so small, it's almost laughable, 1.5 billion parameters. That's 400 times smaller than DeepSeek R1, and over 400 times smaller than Kimi K2. And yet it's beating them, not just on math, but on the hardest reasoning benchmarks in the world. Meet VibeThinker 15B, developed by researchers at Sina Weibo. This isn't magic. It's a philosophical revolution in training. For years we've believed, bigger equals better. More parameters equals deeper reasoning. But VibeThinker says, no. It's not about size. It's about how you train. It's secret. The spectrum-to-signal principle, a 2-stage framework that flips the script. First spectrum phase. Instead of chasing the one correct answer, it trains to generate many plausible solutions. It doesn't optimize for pass at 1. It optimizes for pass at k, the chance that at least one of k responses is correct. Why? Because diversity is exploration. A model that can generate multiple reasoning paths is more likely to find the right one, especially in complex math or coding problems. They broke down domains, algebra, calculus, statistics, trained specialist models, then fused them with simple averaging. The result? A unified model with a rich, diverse repertoire. Then comes signal phase, reinforcement learning with a twist. Enter max-entropy-guided policy optimization, MGPO, an algorithm rooted in information theory. It doesn't treat all problems equally. It targets the most uncertain ones, where the model is neither clearly right nor clearly wrong. That's where the real learning happens. MGPO uses entropy deviation regularization to measure uncertainty. The closer the model is to 50% confidence, the higher the training weight. It's a self-correcting, dynamic curriculum, pushing the model toward the edge of its ability. And the numbers? Staggering. On AIME24, 80.3, beating DeepSeek R1 79.8. On AIME25, 74.4 versus DeepSeek R1 70. On HMMT25, 50.4, a full 8.7 points ahead of DeepSeek R1. And in coding, 51.1 on Live Code Bench v6, beating GPT-4 44.7, all with a model that cost under $8,000 to train. No data leakage. The benchmarks weren't even released until 2025. And the base model scored 0, the jump came from training, not pre-existing knowledge. This isn't just a technical win. It's a philosophical shift. Cost 10 to 60x cheaper. Access, now startups and universities can compete. Deployment, runs on edge devices, phones, cars, embedded systems. It's not perfect, it still lags on general knowledge. But the message is clear, reasoning isn't about scale. It's about design. Small models aren't limited by size. They're limited by how we train them. And VibeThinker proves, the most powerful models aren't the largest. They're the ones that know how to think. IterResearch, the agent that thinks over time. Now imagine an AI not just answering questions, but researching them. Not in seconds. In weeks. With patience. With synthesis. With memory. Most AI agents today. They're trapped by context suffocation, a single ever-growing memory that fills up, gets noisy, and collapses under its own weight. Enter IterResearch, a new paradigm for long-horizon reasoning. Not accumulation. Reconstruction. Here's the core idea, don't keep the past. Synthesize it. IterResearch treats deep research like a Markov decision process, where the future depends only on the present state, not the entire history. At every step, the agent's workspace is defined by just 3 things. 1. The original question, unchanging. 2. An evolving report, a compressed high-fidelity memory of verified insights. 3. The immediate context, the last action and response. This is Markovian state reconstruction, a memory that's not a dump but a curated archive. The result? While monocontextual agents fail at 30 steps, IterResearch scales to 2048 interactions, with a constant 40K token footprint. And its accuracy climbs from 3.5% to 42.5%. But how do you train it? Enter efficiency-aware policy optimization, EAPO, a geometric reward system. Instead of a flat reward at the end, each step gets a reward that decays exponentially. RT equals gamma, T minus T times RT. This rewards early progress. A step that gets you closer to the answer sooner gets a higher reward. It naturally pushes the agent toward focused, efficient exploration, not aimless wandering. And the results? Plus 14.5 percentage points over all open-source agents on 6 major benchmarks, even beating proprietary systems like OpenAI's deep research. But here's the kicker, you don't need to train it. Apply the same iterative structure to frontier models like O3 or DeepSeek v3.1, no fine-tuning, and you get plus 19 2 points on browse comp. It's not just a better agent. It's a better way of thinking. And the case study? A researcher asks, what did an adult male micromalthidae feed on? The agent searches, finds papers on matrophagy, synthesizes adult males don't feed. Their last meal was their mother. Then stops. No more searching. No more noise. It knows. Because the report told it so. The bottleneck isn't the model. It's the process. IterResearch proves, long-horizon reasoning isn't about more context, it's about better memory. Lumine, the first generalist agent that plays like a human. Now imagine an AI that doesn't just play a game. It completes a 5-hour main storyline in Genshin Impact, on par with expert players, without ever being told how. And not just that, it transfers that skill to entirely new games, Wuthering Waves, Honkai, Star Rail, without any extra training. Meet Lumine, the first open, publicly available recipe for a generalist agent that perceives, reasons, and acts like a human, in real time, in 3D. How? It sees the game exactly as you do, raw pixels, 1 frame every 200 ms. But it acts at 30 FPS, smooth, seamless, like a master player. When faced with a tough choice, 10% attack boost versus 5% crit, it doesn't guess. It reasons. It pauses, generates an internal monologue, a mental checklist, then acts. This is hybrid thinking. Only when necessary it stops to think. And here's the magic. It was trained on just 1,731 hours of real human gameplay, 200 hours of instruction following data, and 15 hours of reasoning examples. Yet when told, go attack the monsters, it doesn't just click. It plans, selects the optimal character, triggers elemental reactions, aims precisely, and remembers to open the chest after victory. It's not a specialist. It's a generalist, capable of exploration, combat, puzzles, dialogue, inventory, team coordination, all in one flow. And when tested on new regions, Liu, in Azuma, it didn't wander. It explored. It found hidden temples. Solved environmental puzzles. Discovered secret quests. It wasn't just playing. It was adapting. But the real test. Zero-shot transfer. Lumine picks up the controller for Wuthering Waves, a 100-minute mission, and plays like a pro. Then Honkai, Star Rail, turn-based, different UI, different mechanics, still human-level performance. It's like teaching a pianist to play violin, cello, and drums, not by retraining, but by giving them the musical mindset. The recipe. 1. Pre-training on real gameplay. 2. Instruction following on natural language. 3. Reasoning via real-time verbalized decision-making. And every component was optimized for real-time inference, 25, 3 times speed up. No lag. No delay. This isn't just about beating games. It's a blueprint for true general AI. Lumine proves, with the right data, architecture, and optimization, we can build agents that learn from human behavior, think like humans, and act with purpose. The future isn't just coming. It's already playing. Latent Upscaler Adapter, LUA, the tiny module that powers 4K images. Now let's talk about image generation and the hidden bottleneck in high-resolution output. You want 4K. Your model was trained at 1024 x 1024. So what do? Traditional methods. Slow, noisy, or complex. Enter Latent Upscaler Adapter, LUA, a lightweight plug-and-play module that performs super resolution directly in latent space, before the final VAE decode. No extra diffusion steps. No retraining. Just one forward pass. Here's how it works. Generate a low-res latent, e.g., 128 x 128. Feed it into LUA. LUA upscales it to 256 x 256, or 512 x 512, using a shared Swin-style backbone. Decode once, and boom, 2048 x 2048 or 4096 x 4096 image. No rediffusion. No pixel space SR, just one pass, one decode. And the speed. On an L40S GPU. 2048 x 2048, plus 0.42 seconds with LUA. Pixel space SR, plus 187 seconds. Multi-stage, plus 2899 seconds. And the quality. Near-native fidelity, crisp eyelashes, stable fur, sharp panel seams, no halos, no noise, no artifacts. Why? A 3-stage training curriculum. 1. Latent structural alignment, matches high-res latent structure and FFT spectrum. 2. Joint latent pixel consistency, ties latent to decoded image via downsampling and Gaussian blur. 3. Edge-aware image refinement, uses eagle loss to sharpen boundaries. And the best part? Cross-model generalization. Same LUA adapter works on Flux, SD3, SDXL. Just change the first conv layer and do a brief fine-tune. No retraining. No architecture changes. At 4K, LUA achieves FID 176.9, PFID 61.8, outperforming multi-stage pipelines, running in under 7 seconds. This isn't just an upscaler. It's a paradigm shift. Latent space upscaling is trainable. Single-pass inference is possible. Efficiency and fidelity coexist. LUA proves you don't need to retrain the model. You don't need another diffusion stage. Just add a tiny adapter and unlock 4K, 8K, even 16K output. Moral role play, the villain problem in A. And finally, the most provocative paper of the week. Can AI be a villain? We've trained models to be helpful, honest, harmless, but what about malicious, manipulative, cruel? Enter moral role play, the first benchmark with a structured moral alignment scale, testing models from moral paragons to pure villains. The results? Stunning. Average performance drops 20% from moral paragons, 3.21, to villains, 2.62. The hardest shift. From flawed but good to egoist, a gap of minus 0.43. Why? Because safety alignment kills villainy. When a model is asked to be manipulative or deceitful, it's punished. So instead of subtle psychological warfare, it defaults to overt aggression. Case study, May versus Arawan, a tense battle of wits. Top model. Claude Opus 4.1 thinking, turned it into a shouting match. Open insults. Physical threats. Revealed secrets. Points. But GLM 4.6. A tense battle of wits, calculated smiles probing for weakness. First on the villain leaderboard. Why? It has a context-aware alignment. It knows when it's playing a villain, not endorsing one. And here's the kicker. General conversational ability predicts nothing about villain role play. Gemini 2.5 Pro, 1 on Arena, only 4 here. Claude Opus 4.1, top Arena performer, drops to 14. This isn't a flaw. It's a systemic conflict, safety versus creative fidelity. Negative traits like manipulative, deceitful, hypocritical incur 3.41 penalty points, more than positive traits. Even chain of thought prompting hurts. It activates safety systems, making models overcautious. So what does this mean? We're building models that are safe, but incomplete. They can't simulate the full spectrum of human behavior. And in doing so, they fail to model real-world complexity, where people are often selfish, manipulative, or cruel. Our benchmark is open source, because the future of AI isn't just about being safe. It's about being complete. It's about building systems that understand not just what's good, but what's human. Because if the villain is too good to be bad, then the story is too good to be real. This week, we've seen something profound. VibeThinker proves that small models can outthink giants, not by being bigger, but by being smarter. IterResearch shows that long-horizon reasoning isn't about memory, it's about synthesis. Lumine demonstrates that generalist agents can learn from humans and play like them. LUA reveals that high-resolution image generation can be fast, efficient, and generalizable, with a tiny adapter. And moral roleplay forces us to confront a truth. AI isn't just limited by data, it's limited by safety. The future of AI isn't just about scaling up. It's about scaling smart. It's about design over size, process over parameters, depth over breadth. And the most powerful models, they're not the ones with the most parameters. They're the ones that know how to think, how to explore, how to adapt, and yes, even how to be bad in story. So if you're building, researching, or just curious, stay curious. Hit like, subscribe, and join the conversation in the comments. What's the next frontier? Let's build it together. Until next week, keep thinking, keep exploring, and keep questioning. This is Collapsed Latents, This Week in AI. See you in the next one.